Today I'm going to talk about sort of the gold standard in scientific experiments is often a randomized controlled trial. But in a lot of situations as data scientists, we can't conduct an RCT. Sometimes this is too expensive, our clients don't want to pay for them. Sometimes it would be like wildly unethical. Like if I really wanted to prove that smoking caused lung cancer, I'd have to randomly pick a control group and a treatment group and force the treatment group to smoke for 20 years and then see how many of them died. Like I can't do that. We're going to talk today about some techniques you can use to take data that you already have, observational study data, and make it look slightly more like experiments. And kind of interestingly, some of the math that we're going to go over today, like the versions of it, are what researchers did in fact use to prove that smoking caused lung cancer. So I thought that was kind of cool and a public health for the win. And I'm going to talk a little bit about a repo I've been working on at work with Civis Analytics called PyMatch that does a lot of this for you, and that we're just about to open source so you guys can all use it if you would like. And I'm going to walk through this analysis on one sort of famous data set for this, including a lot of the mistakes that I made as I was doing this, and that I hope I can help you avoid. So we're going to talk specifically, the technique we're going to talk about is called propensity matching. We're going to talk about how to propensity score and then how to match with PyMatch using a specific algorithm of PyMatches. And we're going to talk about some of the mistakes that I made, specifically in making sure that you're validating your matches. And then we're going to talk about how to calculate your results after you've matched. And I have some very strong opinions about how to compare your groups, but I'll talk to you about a couple of different ways to do that. And finally, at the end, in order to do this analysis, we're going to have to make some really heavy assumptions. And so it's really helpful at the end. We've included some functionality in PyMatch to do a sensitivity analysis, which I really recommend to you, because many of these analyses do not hold up that well if your assumptions fail. Spoiler alert, we're going to talk about one of those data sets today. So I want to give you guys an example of that when this doesn't work as well. So the sort of canonical data set for studying this problem is called the Lalonde data set. It involves a job training program that the US government did in the late 70s for welfare recipients. And what they were hoping was to determine whether or not that job training had an effect on the individual's real earnings in 1978. I have a non-randomized control group that was pulled out of the current population survey by the Social Security Administration, and that's just a group of unemployed males in 1976. And you can see here I have just a variety of variables about my groups, how old they are, how many years of education, some indicator variables for race and marital status, and the total of their real earnings in 1974 and 1975. And I'm looking at this 1978 earnings. If I apply a regular statistical analysis to this, I can look at my average treatment effect between the control and the treatment. And here I can see that the control group earned about $6,900 and the treatment group earned about $6,300, which means receiving job training appears to have made all of these people lose $600 in 1978. That did not feel very intuitive to me. I hope it doesn't to you. And we're going to talk about some of the techniques we can use more helpfully to compare apples to apples in these analyses, instead of, say, apples to rutabagas. Here's just an example of that in visual form that I thought was interesting. One of the variables in the data set, we can see in my control group, I have about 20% African American people, and in my treatment group, I'm at 80%. So this is very, very lopsided amongst my control and treatment groups, and this is one of the problems that I want to solve. So I tried to calculate the average treatment effect and measure that difference between control and treatment, but my groups aren't randomly assigned and they just look nothing alike. What I really want is to get a control group that looks just like my treatment group. And the reason is I don't care about the average treatment effect on a random subset of the population. I want to know what the treatment effect was specifically for welfare recipients. And so I'm going to try to construct a group that looks much more like my treatment group so that I can compare them. To do this, we define a different term, which in the literature is called the average treatment effect on the treated, or the ATT. Here I have a yi0, which is my outcome for subject I that was exposed to the control, and a yi1, which is the outcome when exposed to the treatment. And to calculate the average treatment effect on the treated, I'm going to subtract them, and that's my tau. Now, immediately I have a very serious problem. How am I going to observe a person who received the treatment and then simultaneously observe the same person not receive the treatment and subtract the two? I have an awesome solution. A portal gun. If I could travel between parallel dimensions, I could do this super easily. Just FYI, if you invent a portal gun, the rest of this talk is going to be very irrelevant to you. I would use a portal gun. That was the way to solve this problem. But because I don't have a portal gun and I can't travel between parallel universes, the first solution I might come up with is, well, maybe I can just find observations in my treated and control groups that look basically the same. They're about the same age, they're about the same, they're the same race or religion or whatever it might be, one in the control group and one in the treated, and then I can compare those. But even if I have just a small data set, just say 30 variables, and even if I'm just trying to match above or below the median, I end up with 2 to the 30th, or about 1.1 billion possible match combinations, and the Lalonde data set has just 600 rows. So I'm already out of luck. I don't have to give up. I can't match on 30 variables, but it'd be super easy to match on one. I'm going to call this one variable a propensity score, which just measures the likelihood that an observation was treated. To do that, I'm going to take my xi, or the covariates that I know about this subject, and an indicator variable, ti, which equals 1 if the subject was treated and 0 otherwise. And I'll define a function e, which I'll call the propensity score. This measures the likelihood that the subject received treatment. Functionally, what this usually is a logistic regression, where my treatment indicator variable gets regressed on all my other covariates. And that should tell me the probability of treatment given the covariates, xi. Now, if I make the very strong assumption that my covariates are going to explain everything there is to know about my subject's probability of treatment, then I can say that my yi1 and my yi0 are now independent of my treatment given my xi, which implies that they're also independent of my treatment given my propensity score. And this is awesome for me, because now instead of trying to match on all the covariates, I'm just going to try to match on the propensity score. And if I have the same distribution of propensity scores, I'm going to assume that I have a better balance amongst my groups. So that's the math. Now we're going to talk about doing some of this in action. Here I'm building a couple of logistic regression models. One I'm going to call the basic model, and the other the DW model. DW stands for Dihigio Waba, which are two famous researchers that published a paper on this data set. My basic model, all I'm doing is creating a logistic regression on all the covariates I have on the data set, on my treatment. The DW model is adding in some transform variables, including the age squared, an interaction term between education and real earnings in 1974, and a handful of other things. You can see here at the bottom, my basic model's area under the curve is actually better than the DW model. I'm getting about 0.85 for my basic model, but this is not going to be the end of my story. So here's a QQ plot of real earnings in 1974 before I've done any matching at all. You can see here that the two distributions do not match up very well at all. Ideally, I'd like to see all these quantile dots along my red line, which would imply they came from the same distribution. Obviously, they don't. My control group has a lot more money than my treatment group in 1974, and this also helps explain why I saw the treatment effect I did initially. My control group was making a lot more money in 74, and so it's not that surprising that they're also doing so in 1978. So, after I've defined my logistic regression models and I have some propensity scores, I'm going to continue on and do propensity matching. PyMatch will do the propensity matching for you. It's a pretty simple algorithm. All I'm going to do is bin my treatment propensity scores in a histogram based on the number of quantiles you pass to PyMatch. And I'm going to make those cuts so that I have roughly the same number of treatment propensities in each bin. So I might have, say, 5 observations between 0 and 4% propensity, and another 5 between 4 and 6, and another 5 between 6 and 15, whatever it might be. My cutoffs are not going to be exactly equal, but the size of the bins are. And then I'm going to take my control propensity scores as well, and put those into the same bin cutoffs. After I've binned both my treatment and my control, I can iterate over my histogram, and if I have more control observations than treatment in a bucket, then I'll just sample down the controls, and if I have more treatment observations, I'll just sample down the treatments until I have the exact same amount in each bucket. And once I have the exact same amount in each bucket, then I have matched this up, hopefully. Here's the first indication that my basic model is having some issues. If there's a dramatic mismatch in your propensity scores between your control and your treatment groups, specifically here I have a ton of control observations with very, very low propensity. This algorithm struggles to match everything because it doesn't have enough spread amongst the control groups to put everything in the appropriate bins. You can see the DW model is doing slightly better on this, which is great. Now, this is the part that was starting to drive me crazy. Here again is the graph I showed you before. This is just the QQ plot before I've done any matching at all. If I now look at the QQ plot after I've done my basic matching algorithm, we can see that my quantiles are curving even further away from that red line. I went to all the trouble to do this matching, and now my distributions are even worse than they were before, which makes me feel like that. So I went back over this and I slightly tweaked my algorithm. All I'm doing now is just dumping control observations that were below the minimum treatment propensity or above the maximum treatment propensity and matching again. I named this particular function after myself, but I'll give it a better name when I open source it. And now you can see matching on real earnings in 1974, which has improved a little bit. This is my first pro tip to you guys, and a lot of people ignore this step. I think it can be really important. You want to compare your distributions after you've done your propensity match to see if you are indeed getting closer to identical distributions amongst your control and treatment. We can see here that the basic match is doing a little better, but the DW match is doing even better than that. What I can say about this is that it can be an iterative process. It is in your best interest to try out like a handful of logistic models and look at the results in the QQ plot to determine which of these is the best fit for you. You cannot just use AUC, which is what I tried to do initially. Then the second assumption I want to talk about, after you have done your matching, you should have the exact same distribution of propensity scores amongst control and treatment, or as close as you can possibly get. If you are violating that assumption in any possible way, you're violating the original mathematical assumption you made that if you matched on the propensity scores, that you could do an analysis. I struggled with this a handful of times as well, and so I've learned to make kernel density plots of these after I've finished the matching. So once you've tried the matching, make sure that you inspect it as well. Here it is before the matching, and again, we're seeing like a ton more control observations with very, very low propensity. But after I've finished my match, these are basically lining up exactly. This is on the right is a very, very pretty graph. It makes me happy because now I know I can do my analysis. So after I've finished my match, I'm going to go ahead and create pairs out of this data set by sorting on my propensity score. So I'll take the lowest propensity score for control and the lowest for treatment, pair those together, and so on down my list. And then I'm going to take the difference in real earnings in 1978 between those two. And now I can see that my average treatment effect on the treated has gone up. It's now $814, which is awesome. Meshes more with what my expectation was for what job training might do. But I still haven't looked at the sensitivity of this analysis, and I need to pay close attention to that as I go forward. I was looking at the difference, the paired difference here. The reason I made that choice, you could do this analysis in a variety of ways. Some people have used regression as well and looked at the coefficient on the treatment indicator, which is totally a valid way to do this, absolutely. I prefer this particular method because the literature on sensitivity analysis is a lot more thorough on a technique like this. And so there's a lot more developed sensitivity analyses for this kind of thing, for this kind of study or technique. All right. So I made this assumption at the beginning. I said, everything I know in my covariance X is going to explain all the variability there was in treatment assignment. How much does that even make sense? We can imagine two subjects in my data set, J and K, that have the exact same covariance, but might have a different probability of treatment based on something I didn't observe. Maybe there's something that's missing from my data set that matters a lot to treatment assignment, and I don't know about it. It's a blind spot for me. So one way to look at this mathematically is to calculate an odds ratio between these two individuals. If I say that they have, assume that they have the exact same covariance, and I look at the odds to treatment for both, if my assumptions are correct, their probabilities of treatment should be equal, and the odds between them should be 1.0. But as they get further and further out of whack, I'm going to bound that by this constant gamma. And I'm going to take a look at different values of gamma to see how that might affect my analysis. That's going to change my p-value on this one. So there are other researchers who've written a lot of excellent statistical tests that look at the impact of gamma using a Wilcox-Stein rank test, looking at matched pairs. And typically what you would do in a sensitivity analysis is consider like a range of gamma values from 1.0 to 1.5 or 2, and see what effect that has on your p-value. As your gamma gets larger and larger, the range of your p-values is going to get wider and wider until it's no longer really informative. So, on the Lalonde dataset itself, this kind of blows my mind because it barely gets mentioned in the paper that everybody cites. But even if my results are exactly, or excuse me, if my assumptions are exactly correct, my p-value is still 0.29. I don't have a statistically significant result here. I have worked with data at Civis that does have statistically significant results, but this particular one does not do that. I'm considering gammas all the way up to 1.5, and the column you really want to pay attention to here is my upper bound. This is my worst case scenario on my p-value, and you can see it degrades like quite quickly here. This piece of the analysis is something that I saw not getting a lot of attention, and so I just wanted to bring that up to you guys as well, and this is something that I've implemented in PyMatch as well that you could use. And that is all I wanted to talk about today. I think we probably have time for questions.
Have you ever considered the income of a person who received the treatment? But what happened if he didn't receive the treatment? How much is his income?
So, if I'm understanding you correctly, you're saying like income is a covariate that I could match on? Is that? Because the earnings in 74 and 75 are included in that.
Yeah, now you are comparing the income between the people who receive the treatment and people who don't receive treatment.
Yes.
So I'm wondering whether you can calculate the income of a person who received the treatment, you know the income of the person who received the treatment. And can you predict the income of the person if he didn't receive the treatment?
I'm afraid I don't
Yeah, it's not
understand.
the purpose of this
So,
study, but it's,
got it.
it's a question.
That I'm sure there would be many different ways to do this analysis, and certainly paying attention to whether it helped the individuals that received the treatment would be the most important. So if you could make the case that they were earning more money, that would probably be more important than comparing them to a control, comparing them to themselves, you mean?
Okay.
Excuse me. One more over here.
Thank you. So my question is, how will you approach this in a case with several mixed treatments?
In a case with several treatments?
Yes,
Um,
potential
that,
treatments. Yeah.
that is a phenomenal question, and I don't know how I would do that. I have not read any literature about doing that specifically, but that is an interesting idea.
But how about as a general strategy? How would you start delving into?
Again, I'd have to tell you it's an interesting question, but I don't have a firm idea how I would approach it off the top of my head right now. Yeah.
I'm not a statistical professional. Do you feel like you could put together a cheat sheet for when this approach, sort of what prerequisites there are for this approach being something you should try and when it's inappropriate?
Yeah, absolutely. I think a lot of that has to do with the sensitivity at the end. Will give you a functional idea of how this is working, and that those functions are built into the repo, would tell you. Yeah, absolutely.
Thanks. This is really interesting stuff. I was wondering, at the end, when you get the sensitivity result, and it is maybe disappointing if you're looking for causality, like what would be your next step to iterate? Like, do you just throw up your hands and say, this is impossible, we don't have causality? Or is it possible that, like, with further feature engineering, you actually could, like, at what point can you feel confident that, like, there is no causality?
Right. I would suggest that, like, iterating even further on different propensity models might help with some of that, especially as you get better and better matching between your covariates. But if it's, I suppose, like, the more iterations you do on an analysis like this, like, eventually you'll find some statistically significant result. But I would be skeptical of that to a certain extent. I think this is a reasonable technique to try because we don't have a lot of others when we don't have randomization in our data, but we should also be cautious about it. So I would also be cautious about, like, doing this many times until I find a statistically significant way to do it and then just asserting that one, right?
I had a quick question about when, or what's the process like for releasing this software as open source at Civis?
That is an excellent question. My boss has just told me, like, a couple of days ago that I could do this, so I need to check back in with him and figure out how quickly, but I'm assuming in, like, a few weeks you'd be able to find this at Civis Analytics/PyMatch. Yeah.
Great, thanks. And let's thank our Pete Skipper once again.
Thanks, everybody.